Let's move on and study the bending of beams now. There are several different potential failure modes for a beam. There's the simple fracture type, that's part A there in the figure, where the beam simply breaks at some point. Of course, if a beam is simply supported with a load in the center, then the maximum moment is in the middle of the beam, and that maximum moment is what causes failure. In fact, in a beam, what causes failure most often is the moment load within the beam. And you can think of the moment load, remember we had shear and moment diagrams, you can think of the moment load if you want to understand it. Imagine that there's a hinge somewhere in the beam. So the beam flexes, okay, so it's got some hinge point in it. The moment in the beam is the amount of torque at that hinge that would be required to keep the beam from moving down, see? And you can imagine a hinge at any point along the length of the entire beam, and however much torque is required at that hinge to keep the beam horizontal. That's the moment in the beam. Another failure mode for beams is where there is yielding for part of the beam, where the load is so large that the beam excessively stretches and yields. And a lot of times, of course, that'll happen on the lower flange, because if you think about it, it turns out that actually the upper part of the beam is in compression, the lower part of the beam is in tension. We'll talk about that more in a minute. But if you put too much load on, the lower flange yields and the beam is permanently deformed. There can also be crippling or buckling or wrinkling. There's several different phenomena like this where the material sort of begins to fold up. And of course that's in compression. In this case, on this item C, the upper flange has crippled here, and that's a failure mode. The beam can no longer support the load. In fact, the beam's capacity usually goes down, and if the same load is applied, the beam fails catastrophically. But this is one way that the beam can fail. The web is the section of the beam between the two flanges that connects the two. It's not particularly strong. Its job is really to separate the flanges out to give the beam strength, and so that the beam can take more load. Now this web can wrinkle if the load is too high and if the geometry is just right, rather than the flanges potentially crippling or yielding. The web of the beam can wrinkle depending on the beam dimensions, and this is another mode of failure for beams. If we think about how beams bend when you apply a load, it's helpful to think of how the beam will deform. Of course, a load downward will deform the beam downward. If you have a load downward and one upward, then you've got to figure out which one sort of wins and causes sections of the beam to go above or below its initial position. But certainly a beam bends in order to support the load, because what happens is when you apply a load to the beam and the beam deflects, stress is developed within the material, and it's that stress that generates the moment in the beam and the shear that supports the load, or supports the required static load to compensate for the external applied load. So when a beam bends, if you think about it, if you have a straight segment and you bend it like I mentioned, the top section has to get shorter and the bottom section has to get longer. I should say the bottom and top surfaces get shorter and longer. And the reason for this is because of the deformed shape of the beam. Now the neutral axis is a very special axis along the length of the beam. It's where there is zero strain. And if there's zero strain, that means there's no stretching of the material, therefore there's zero stress in that section of the beam. Now most times it's in line with the centroidal axis. That's not necessarily always the case. When the beam stops behaving linearly and is behaving non-linearly, then the centroidal axis and the neutral axis may not coincide. But for what we're doing, we're only interested in the case when the beam deforms elastically, not when it deforms plastically. And so for our purposes, the neutral axis and the centroidal axis will be on the same line. The equation we will use for calculating the stress in the beam is sigma, because it's a bending stress. It's a normal stress. You're trying to either pull the material apart at the bottom where it's stressed, or you're trying to push the material together at the top where it's compressed. MC over I, this normal stress, is how we calculate it. Now we have to be careful about this. M is the moment within the beam. Remember when we made shear and moment diagrams, that moment M is what goes in here. It's what I was describing earlier. If you imagine a beam that's pinned at various points along the length, how much torque is required to hold the beam in position. Well, that's the moment that goes in here. That's exactly what we get from a moment diagram. We've got that torque or that moment along the entire length of the beam. C is the distance from the centroid to the outermost fiber, and I is the second moment of area. It's the moment of inertia of that cross section of the beam. So this is how we calculate the so-called bending stress. And this actually gives us the maximum bending stress that the beam experiences because it's at a distance farthest away from the centroid. So understand that the stress is distributed across the cross-sectional area of the beam. And we'll see how that's distributed in just a moment. Some restrictions on this formula. The beam has to be stable. If we've got wrinkling or crippling or any of those things or buckling, this formula does not apply. It doesn't work anymore. The stress in the beam also has to be less than the proportional limit everywhere within the beam material. So in other words, the beam has to behave like a linear spring, otherwise what we're doing here doesn't work. Another restriction on this equation is that the material the beam is made of must be homogeneous. You can't have variations in the material properties, otherwise this equation doesn't work. The beam also is assumed to be long and narrow, and that is important for this equation derivation. It's just because the stress needs to be not uniformly distributed, but we can't have variations in the stress from the applied loads. The cross-section has to be uniform, so you can't have a beam where the cross-section is varying along the length of the beam, otherwise again this equation doesn't work. The beam has to not twist, and the beam has to be essentially straight. So we're only talking about very small deflections of the beam. If the beam is deflected a lot, like in that exaggerated picture I had a moment ago, again this equation will be somewhat inaccurate. So how is the stress itself distributed? Well, not surprisingly, as you move farther and farther from the neutral axis, where there is no stretching of the material, as you move farther you find more and more stretching, so more compression at the top of the beam and more extension in the tensile lower section of the beam. And of course I'm thinking of a beam, that's got a load acting down on it, typically from gravity or something. And so basically the stress is just distributed linearly from top to bottom. And so the maximum stress occurs at what we call the outer fiber, the upper and lower surface of the beam. And the reason for I-beams being designed with the cross-section that they have is so that the most material is put in the area that has the highest stress. This makes an efficient beam, a beam that can carry a lot of load. Another really important thing to understand about this stress distribution is that the integration of this stress across the entire area, across the entire cross-sectional area, has to generate the moment M. So if you add up all the little stress in all of its little areas, which is what integration does, right? If you add all those up, the net result of all this stress over the cross-section has to be the moment load at that section of the beam. So that's a constraint for the stress, and that's why the stress and the moment are related to each other by the equation you saw. If we want to calculate the stress at some other point than the outer fibers, of course that's usually where we care about things the most, because that's the point where the material is going to start to yield or fail or whatever. But if for some reason we need the stress at some other point, then we can scale the maximum stress, since it is linearly distributed, across the cross-section of the beam. So the actual stress at some other point away from the neutral axis but not at the outer fibers is equal to the maximum stress multiplied by the ratio of the distance from the neutral from the neutral axis up to that particular area where you want to know the stress, divided by the maximum distance, C. So if we take these two equations and put them together, then what you'd realize is that you can calculate the stress at any point by just my over I. So sometimes you'll hear me talk about MC over I. In that case I'm talking about the maximum stress at the outer fibers of the beam. Sometimes you'll hear me talk about my over I. In that case I'm trying to calculate the stress at some other point besides potentially the outer fibers. Now another thing to understand is that if the beam is not a I-beam like we've seen so far, then the neutral axis is not kind of in the center of the beam, right? It's up higher. Say it's a T like this. So it's up higher near the cross part of the T. Therefore the distance from the neutral axis to the outer fiber depends on which outer fiber you go to. If you go to the top it's not very far, but if you go to the bottom that's a much longer distance. And so what that means is that the normal stress, the bending stress, at the bottom of this beam, at the bottom of the T, is going to be higher than it is where we've put the most material at the top. Doesn't mean that this beam can't be useful for some applications. It just shows you why you need an I-beam shape in the case of, you know, a beam. It's efficient in the case where both the tensile and compressive stresses cause the same amount of trouble for the beam, or you have to design against both and they're equal. Well, in this case, this would be a great design for a material that is not good at compressive stress but is really good at tensile stress. Now that's not most common. The more common configuration is where the material is good at compressive but not tensile stresses. Concretes and brittle materials fall into this category frequently. And so if you took this beam and you turned it upside down, where the straight section of the T is now at the top, well, now that section is going to be in compression. And so you'll still have a high load, but you can reinforce, you can add material where it's needed in the flange where the material is not good at tension, because if this is upside down, obviously the flange portion is going to be in tension. So that's one strategy for overcoming the imbalance in strength that a material has in tension versus compression. But of course you have to be very careful about buckling in that case.